Okay, there was a question on the bricklaying robot. The question is, does it completely eliminate the labor or will it work in tandem with labor? Do you think it can be used in the industry today? So if you ask my opinion, I think there is a lot of potential for that. That's the reason why Shapoorji Pallonji is interested in testing it. So that testing is going on right now. And currently, there is still some manual element. You need to load the bricks with the mortar. So you must have seen that in the video. So there is some involvement for labor, but a lot of physical the activities have been eliminated, like lifting the bricks, placing it, and so on. And also now you can, we were earlier constrained by the weight of the brick. The weight of the brick has to be less so that people can lift it. Now you can use larger blocks with this kind of machine. So there are a lot of possibilities. There are a lot of ways to improve the productivity rate in masonry construction. And we need to start thinking about these because uh, we cannot keep up with the demand the way at which we are doing the construction today. Okay. Yeah, I think we will start once again. So let me quickly summarize what we have done so far. Can you confirm you're able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So far we have seen some potential for automation in the construction industry. We saw some examples where automation has been successful in the mechanical engineering domain, and then we have seen some examples in the construction domain. And then I briefly introduce you to the idea of a control system where we can make systems which can do certain physical activities using sensors, controllers, and actuators. And I explained how it works. The sensors communicate with the controller using voltages and currents. Similarly, the controller communicates with the actuator, sends signals in the form of voltages and currents. But the most important thing is the software. Hardware is simple, straightforward. This is something a lot of our students do as hobby projects. Right, to make things, and even in our physical version of the workshop, I mentioned that the participants play with sensors, the controllers, actuators. But the important thing is the software. The intelligence is in the software. So I may introduce you to some of the stages where we can where we can use machine learning and artificial intelligence in sensing, data analytics, in control logic, and continuous learning, through feedback. So these are some of the areas where we can apply machine learning techniques. So now we are going to discuss about machine learning in more detail. To summarize what we said about machine learning, we started discussing about how human beings learned, and we saw that an important aspect of human learning is improvement of performance with experience. In machine learning also, the objectives are exactly the same. We want systems to improve continuously with experience. And here I've replaced experience with data, because that's how all the machine learning techniques work today, using data. So this is the broad objective of machine learning. And we saw in the case of human learning, an important aspect is acquisition of knowledge. But acquisition of knowledge alone doesn't make a system smart. If acquisition of knowledge is the sole criteria for intelligence, maybe a library would be the most intelligent building, because it has a lot of knowledge, a lot of books are being continuously added, but the library doesn't become smart. So acquisition of knowledge is not a sufficient condition for intelligence. We need to acquire knowledge in a form which the computer can make use of to improve the performance. So that is the challenge. And the acquisition of knowledge, we saw in the case of human beings, we can get data, get knowledge from other sources, from books, from other people, or through self-discovery, through knowledge discovery. In the case of machines also, we have exactly the same thing. We can get knowledge, machines can acquire knowledge from other sources, as well as by discovering knowledge by itself. And the way it works today, we provide data in the form of training examples. Today, we are mostly looking at statistical learning techniques. Later on, I'll talk about all the different learning techniques. But the most successful has been statistical learning, where data is provided in the form of training examples. And then we extract knowledge from this data and generalize it so that it can be used in situations which need not be exactly the same. So we want the system to work even in situations which are slightly different, using the knowledge it has gained from previous experience. So now if you compare a machine learning program with a conventional procedural program, conventional programs produce the same output all the output all the time. It doesn't improve with experience. So take this example of this Hello World program. When you start learning C programming, this is the first program you write. It's in the book by Kernighan and Ritchie. They have given this program. This is the first program everybody writes to learn C programming. So you write the main function, you say printf hello world. It prints this on the console. So you compile it, you create an executable called hello.exe, you run the double click on it or run it. It prints hello world. So today if I run it, it prints hello world. Tomorrow I run it, I get exactly the same output. Output does not change. Suppose I don't like the message. I want the message to be changed to good morning user. There is no way the program can accept feedback from me. The program cannot understand that I don't like this message. I want a different message. And there is no way I can communicate to the program. And the program has no way of modifying its output by itself. All you can do is talk to the programmer. The programmer will change the source code. Instead of printf hello world, you write printf good morning user and recompile it. You create the executable. Now when you run the new executable, you get a different output. So the conventional program does not have any mechanism for accepting feedback, and it cannot improve by itself. The improvement has to be done by the programmer. Whereas a machine learning program, we accept feedback in the form of training data, and using this data, we modify the procedure so that next time we get a different output. A simple way you can do this is change the program to read the message from a data file. So instead of saying printf hello world, the first line would be read a data file, what is the message to be printed, and you say printf that message. But then if you put good morning user, Everybody who runs it any time of the day will get the same output, good morning user. So what is the next step? Instead of treating the string itself, reading the string itself to be printed, you can read a rule from a data file. In your data file, in your text file, probably I will say, if it is morning, you print good morning. So you read a set of statements, if condition, then action. So this is the idea of a rule-based system, which became popular in the 1990s, 1980s, I would say. So I'll talk about this rule-based system later on. But today, people don't use rule-based system. Expert systems are dead. Nobody uses it anymore. But this idea of compiling knowledge from data that came from this experience from the 1980s and 90s, that is, you can read knowledge from data files and you can modify the behavior of the program using data. So this is a very fundamental idea. The knowledge is not hard-coded in the program. It's not in the source code of the program. You separate the control from knowledge, and knowledge is in the data file. So this is that important concept which came from the experience in expert systems. That is, knowledge can be obtained from data files. And there have been a lot of developments. And as you know, in the 1990s, when I did my PhD, I completed my PhD in the area of something called case-based reasoning, applied to conceptual design of buildings. And my first job was in Infosys. So when I went for interview in Infosys, so somebody asked, what was your area of PhD? I said it was artificial intelligence. And they said, artificial intelligence, who uses artificial intelligence? It's obsolete. This is in the 1990s, 1995. There were people in a software company which thought that artificial intelligence is dead. It has no application. It's obsolete. And then I started explaining, no, it's not dead. There are a lot of places where you can apply this. And people wouldn't believe me. Anyway, I got the job and I didn't work on artificial intelligence when I was in Infosys. But after that, you can see how much it has changed. Today, everybody is talking about artificial intelligence. There has been a big leap from the 1995 to today, mainly because of the improvements in hardware. Today, machines are capable of doing much more that was possible in the 1990s. And it really improved the capabilities of machine learning systems. So what we are capable of today was not possible mainly because the hardware was not that good at that time. So today you see a lot of intelligence systems, handwriting recognition systems, voice recognition system, face recognition, which could not even be imagined in the 80s and 90s. But we are still not there. The kind of systems people imagined in the 1950s and 60s, thinking machine which can do all kinds of solve all kinds of problems, do all kinds of tasks. Today you hear the terms general AI and narrow AI. General AI refers to artificial intelligence, which can be applied to all kinds of problems. Generic programs which can do everything. This is the idea from the 1960s. Machines which can think like humans, do everything that humans can do. You see a similar thing in the case of robots, where generic robots which can do everything, and automation system which can do special tasks, special purpose robots. And you will see that in the case of AI today, all the success stories are in narrow subdomains where we are able to formalize the machine learning task for specific sub-problems. There are certain types of tasks where we have been very successful, I'm going to talk about that, the specific type of problems where machine learning has been successful, but we are nowhere near this idea of a generic AI. And then now people are also talking about super AI, where the capabilities are much more than what we have today. So the current status is that there are certain kind of sub problems where we can use machine learning and artificial intelligence. So these are some of the specific tasks where we can apply machine learning quite comfortably today. We call it as supervised learning tasks, unsupervised learning tasks, and reinforcement learning. You have three types. I'm going to explain these three different types of learning tasks. So in a supervised learning task, we have a set of input variables and a set of output variables. So we have data which consists of input and output. And then we have a set of possible relationship between input and output. It's called as the hypothesis space. And the learning algorithm finds the best hypothesis that fits the data, maps the input to the output. And this is done using feedback, which is using training data. So to understand this concept, we will do a small exercise. So this is that exercise. This is like a small puzzle, the kind of question you get in analytical reasoning. Simple exercise, everybody can do it. So you can just click on that link in your on the website. So you have already done the two exercises. So we are doing the third exercise. So you can click on that link and you can answer this. A simple exercise and pattern recognition. It will take a couple of minutes. I'll just wait for responses from you. The first one is simple, find the missing number. I'll wait for some more time so the others can also complete it. Okay, so let us discuss about only 30% have submitted, but let us just discuss. So what you have really done is supervised learning, right? This is exactly what a computer does when it does supervised learning. Take the first example. You have a set of training data. You have the input, you have the output. So this first column here, that is the input 0, 10, 18, and you have the corresponding value in the second column, which is the output variable. Let's call it as y. And you try to find out, and then now we have test data. So this is the training data. The first three data points is the training data, which is used to find a relationship between the input and the output. And the last one is the test data, in which you are trying to predict the output when only the input is given. When the output is not given and the input is that we want to predict. So we're using the data, training data, we find a relationship. And this relationship is used to predict the case of test data where you don't have the value for the output variable. So now let us look at what you have given for this first exercise. So almost all of you have given 42 as the answer. Yeah, this is easy to see why you get 42. You look at this, you multiply by 2, add 2, you can get 22, you get 36 plus 2, 38. So 2 times 20 plus 2, 42. So it's understandable. You get 42. But now I'm going to surprise. Did somebody say something? Yeah, if you are not asking any question, you can mute it. Okay, so we got a lot of answers. Most of it is anybody speaking? Okay, I'll mute all the participants. 1 second. Okay, I'll do that. Okay, now I'm going to surprise you. So the majority thinks 99 responses, 100 responses, 87% of people think it is, the value is 42. Now, if I say that the value is not 42, you'll be surprised, right?
Yes,
Let's
sir.
take the next one. 64. The question is find the missing numbers. So you saw 0 cubed, 1 cubed, 3 cubed. So you take 4 cubed, it is 64. Now I'm saying your answer is not 64. Most of you have written 64, but I'm saying the answer is not 64. Might be surprising to you. Now, let me come back to what we discussed. So learning algorithm attempts to find the best hypothesis that maps input to output. This is exactly what you have done. You had a certain hypothesis space. You have a definition of the hypothesis space. So in your mind, all that exists is probably a linear relationship, a cubic relationship. These are the best hypotheses which you could find. But how do you know that is the best, that is the actual relationship between the input and output? In fact, there can be infinite number of possibilities. There are infinite number of possible relationship between the input and output, and you just found what is the simplest one. In fact, you followed what is called as the Occam's razor, which we are going to discuss later. So what you have done is exactly what a machine would do. It will try to find the best hypothesis for mapping the input to the output. This is exactly what a supervised learning algorithm does. But it does not mean that it has found the best, it has found the right relationship. Probably the relationship is different. By chance, it just happened that there is a linear relationship or this cubic relationship which you have found. Similarly, for all the examples which you have done, you are trying to find a hypothesis from your set of possible hypotheses. That is, you are searching in a hypothesis space for the best hypothesis. It may or may not be the actual relationship between the input and output. Just because it fits all the data doesn't mean that for a new data point, it is going to follow the same relationship. Okay, so this is to bring to your attention some problems with supervised learning. So all learning is simply searching for a hypothesis from a set of possible hypotheses. Okay, let's move on. So we have mainly two types of supervised learning tasks. The first is called classification. The other is regression. What you have done, the exercise which you have done just now is just a regression. We'll come back to that. First, let's talk about classification. This is a problem which those who are not familiar with machine learning might not know. So I'm going to spend some time explaining this problem. Regression is something which everybody has done. So that is more widely known, but classification, even though it has a lot of application, may not be that much familiar to people who are not familiar to machine learning. So I'm just going to explain this. In a classification problem, just like in supervised learning, we have set of input variables and set of output variables. This is a supervised learning task. So these output variables are class labels. These are discrete variables. These are called class labels. In the case of regression, we have usually continuous variables. But in the case of classification, we have discrete variables. We call as class label. Give some example, it becomes clear. Input variables can be continuous or discrete. And the task is to predict the output for a given set of input variables, just like in the regression, but we want to predict what is the class label. Take an example in worker activity recognition. Tomorrow you are going to have an interesting case study on activity recognition. My student Aparna will present a case study on activity recognition. But to introduce you to this idea today, imagine we have workers on a construction site and they're doing different kinds of activities. They are lifting bricks, placing bricks, transporting material. They're doing different things, and some of them are just sitting idle, smoking, or whatever, sleeping. And we want to find out what the worker is doing. I don't know whether it is ethical or not. We leave out all the ethical issues related to that. But we want to supervise. We want to find out what these workers are doing. And I don't want to put too many supervisors to find out what the workers are doing. We don't want to put too many spies. We want to do it maybe discreetly. So we put some sensors on the workers. Put some sensors. There could be accelerometers. There are different kinds of sensors available. So you put it on their arms, on their shoulders, different parts of their body. And let us say these sensors send this data in real time. You have some communication device which will send the data. So every, some 10 times per second or 100 times per second, this data is getting uploaded to a server, and the construction manager or supervisor sitting in an office looking at the data, and he wants to find out what the worker is doing. Okay. And we want to find out what the worker is doing by looking at the patterns you get from the sensor, from the accelerometers. So let us say if you plot it, you might get some signal like this. It doesn't make much sense to you because our eyes are not good at recognizing patterns with this level of details. But machines have much more capability in recognizing patterns. So we get this kind of data, time series of accelerometer data, which you get from workers. And using this data, we want to find out whether the worker is idle or whether the worker is working. So here we have two class labels. We have two classes, idle and working. We have a series of times that accelerometer data, and using that data, we want to predict what is the class label, whether it is idle or working. So this is the classification problem. Okay. So the output variables are class label. Depending on the application, it could represent anything. In this case, it is an activity. Class label could be an activity. The person is idle or working or doing specific tasks. And the input variables are, in this case, accelerometer reading. And we want to predict what is the class label, whether the worker is idle or worker is working, by looking at the time series data. So this is the problem. So what to do this, we need, so this is a supervised learning task. So we need to have some training data. So if you come back to what I said about rule-based reasoning, you might say that you might put some rules saying that if the accelerometer reading is above this, the worker is working, otherwise he is idle. So you can develop a rule-based system, a set of rules to determine whether the worker is working or not. But these tend to be very brittle, very unreliable. It's very difficult to find rules that are accurate enough to provide predictions correctly in unseen situations. So that's why people don't work with rule-based system. The other option is you give some training data. You give to start with, we don't know whether what patterns corresponds to idle and what patterns correspond to working. So we take a lot of data. We make the workers do work, make the workers sit idle, and we collect the data and manually label the data points. We label the data points as idle and working by uh, actually observing what they are doing. So that becomes your training data. And then the machine learns what are the patterns in this data which correspond to idle and what are the patterns which correspond to working. So this is the process of machine learning. And once this model has been learned, given a new data, without the class label, with only the input variables, the system will be able to predict what is the class label, whether it is idle or working. So this is the problem. So we'll do a small exercise to test what you have understood from what I described so far. So this is the next exercise, worker activity recognition problem. Okay. So this is exercise number 4. You click on it and you can take this quiz just to find out what you understand about the classification problem. So the first question is activity recognition problem. What is the output variable? Second is how many input variables are there? If you have two accelerometers placed on the workers, how many input variables are there? You have options 1, 2, 3, more than 3. Okay. So you can take a couple of minutes to answer this. These are simple exercises which you can easily complete. it helps me understand what you understand about what I have explained. Okay, about 30% I've already answered. So let's look at some of the answers. Okay, so most of you have written correctly. So the output variable is the class label, idle or working. That's good. I think all of you have done correctly. So that is right. Okay, I think it's just most of it is just same correct answer. Different versions of the same answer. Let's look at the answer. How many input variables are there? You have two accelerometers, and most of you have written you have two input variables. Some people who have written three, I don't know why, and 20% have written more than three, and some people have written one. So what is the correct answer? The correct answer is not 2, it is more than 3. Why? I'm going to explain. We have two accelerometers, but it's not just the absolute value of these accelerometer, the accelerations that are used to classify whether it is idle or working. It is a whole series of data. You have a time series with just one data from the accelerometer. We will not be able to recognize the pattern. You need a whole series of data, probably over a few milliseconds or the fraction of a second. Maybe in 0.1 seconds, we have some 100 data points which have values for the acceleration for the first sensor and the second sensor. So you have a series of uh, values from each of these accelerometer, and we need the entire series to determine what the worker is doing. So the number of input variables. So the number of input variables is more than 2. So if you have 100 the points in your time series for the first accelerometer, another 100 for the second accelerometer, we have 200 input variables, and we use all these 200 input variables to predict whether the class is idle or working. Okay, so it is not 2. Now, later on, we will see, we might be able to extract some relevant features from these input variables. It is not the absolute raw data itself, which will be used for the classification. It's it could be some patterns which you extract from this data. So it could be some features which you extract. We'll see that concept later on. Okay. So now, so just to refresh what we said, in a classification problem, we have a set of input variables and we have an output variable, which is typically a class label. And from the input variables, it has to form a relationship to map the input variables to the output variable. So that is the process of learning. And once it has learned that model, you can use that model to predict what is the class label when you know only the input values. To take another very common example, very famous example, that is image recognition. Today we use face recognition. There are a lot of applications, even on your mobile phone. We are using AI technology to log into your device. You just show your face, it knows to recognize your. That is a face recognition problem. It's an image recognition problem. And if you want an example right from the construction the site, we can think about a mobile robot which can identify an equipment on a construction site. The robot has to do a certain task. For example, it has to insert a bolt into the component, and it needs to identify this the object. So that is an image recognition problem. So imagine you have a mobile robot which has a camera, exactly like that Spot from Boston Dynamics. You have a camera which is getting images and it has to recognize particular devices. So it becomes an image recognition problem. So in this case, the class labels are for each equipment type, we can have one class. So we want, you can have binary classification in which, suppose you are interested only in a particular type of equipment. You can have a binary classification problem where the first class is the particular equipment you are interested in, other classes something else. So you can have one or two or more output classes, and the training data will be the camera images that are correctly labeled. So you show a number of pictures of the equipment. So you say, these are the equipment that I'm interested in. You show an
So unable to hear you, sir.
So you're not audible.
Are you able to hear me?
Now it is back.
Sir. Now it's okay.
Hear you now, thank you.
Okay, I thought there was a network error. Okay, so let me continue. Can you confirm again you're able to hear me?
Yes, sir.
Yes, sir.
Okay, okay, thank you.
Yes, sir, you're audible.
Okay, so this is a small prototype we made some years back. This was an undergraduate project, a BTech project. We tried to experiment with automated assembly of steel structures. So we have a scaled prototype of a steel frame, and the columns are made of these small components. This is a scaled prototype. So I have shown two steel modules, and then we have a plate which is used to connect the modules together, and we assembled this whole steel frame. So this was done manually. We did this manually, connected it. Some students connected it manually. but we wanted to automate it. So this is a small prototype which a group of students made. So you can see there are some motors using a rack and pinion kind of system. We can produce linear movement. So this can move in the X direction, Y direction, and Z direction. And you have a small camera here with a tool here, which for inserting the bolt. So you have this camera, and this camera is pointed at this object. And we want to find out the position of the holes where the bolts have to be inserted. So this is a small prototype which our students made using computer vision. By taking images, you locate the position of the holes and you insert it. And it's a working prototype, it works, but I wouldn't say it is 100% successful. We have a lot of problems because of the precision. In mechanical engineering, in automobile factories, everything is very precise. But in construction, fabrication tolerance is not that great. So you will see that, the holes are not perfectly aligned. When you put the plate, you'll see that the bolt does not easily go through. But we still did some experiments with it. It has been partially successful. That's just to show one example of where we can use image recognition. By taking pictures, by taking images, you train systems to recognize objects and features and edges, and use that to do some automated action like robotic assembly. So this is another example. Now I'll show you another video of a more sophisticated equipment which we fabricated. This is the earlier one was a scaled prototype, but this one which I'm showing is a full-scale prototype. We have a device which can take about 2 tons of load, and it can assemble steel columns and beams. I'm just going to show this video. So let me explain what they are doing. So this is a steel module similar to the small steel modules you saw in the earlier, the smaller prototype. And this is a machine. So we load it into the machine. It is locked. This is manual. Now the machine is lifting the module. So you can see it is going up. So now examine this hole here. Right, you can see a pin has been inserted. A pin has come out. This is called the holding pin. So it has connected this module. And now you can see, this lifting base is coming down. It's going down. It's lowering. The machine itself is not moving. It's still on the ground. But the module has been lifted. It's held up by the holding pin. We loaded another module to it, locked it. Now it is going up. It is lifting up. You can see the pins are stacked, and these are pushed one by one after each module. So now it is going up. It has made contact with the previous module. Now you can see the pin is going and inserting into the module. So you can observe here the pin is going to come here. Yeah, actually it is already connected. So now it is lifting up. So after many, you can see that the structure grows up. This is called push-up construction, vertical. The structure is lifted vertically. The machine is staying on the ground, but the structure keeps growing up. Okay, and you can see it is coordinated lifting. Two columns are lifted simultaneously, and these are automatically connected using pins. Okay, so I stop here. So this is an example of an automated construction system. It is now, this doesn't use any machine learning or artificial intelligence. We thought we can do away with it without using any machine learning. We can automate the whole process. And I would say this is also partially successful. I wouldn't say fully successful, because what has happened is, here in the earlier project, we had to detect the holes because we don't know exactly where the components are. But in this particular machine, we load it at a precise location. So we thought that it's just as simple as inserting a pin to connect the modules. But in actually what happened was it didn't work that well. So one day when we were doing this experiment, there was a slight misalignment. So the pin got stuck. It didn't go completely inside. It got stuck. And the machine didn't realize that it is stuck. So it started moving. The pin got bent and there was a lot of damage. This whole thing had to be assembled again. So what I'm saying is that with image recognition, with machine learning, we can make these machines smarter. It works without all this, but it doesn't work that well. And under uncertain conditions, when we have uncertainty in the fabrication tolerance and other things, there are small deviations from the ideal, which we may not be able to detect that easily. That is where we have to use machine learning, where we might have to use image recognition or use other kind of sensors to determine whether everything is going on smoothly. Okay, so it is already 4:40. So I won't go into the next topic, regression, right now. I'm going to stop now. So if you have any questions, you can ask.
So what is the role of augmented reality, sir? See, you talk about image recognition, but the major problem in the construction post-COVID is the object recognition, because supervisor is not available. As you correctly mentioned, that labor migration happened and all those things happened on construction side. So object recognition plays a very important role. Maybe object is a equipment, maybe the object is a material. So how do we solve that problem with respect to that particular object recognition with respect to the equipment or with respect to the material?
Yeah, no, object recognition, just like face recognition, activity recognition, it's a recognition problem. It is exactly in the domain of machine learning. So let us say we want to recognize a particular object. It's exactly like recognizing a face. You show a lot of pictures of the object. So the machine makes a model. It's trained using these images. And then in general, you need to give positive and negative examples. So you could show pictures of the objects and pictures of other objects. So it knows to distinguish between the different objects. So, but with training, you can definitely do it. Today, this is one of the success areas of machine learning, object recognition, image recognition. Of course, it's still not easy to train. Some of my students worked on it. It requires some effort to train it properly, to input the right type of images, to make sure it has learned properly. All that, there is some effort that is required. But this is, I would say, a solved problem. People have already done this already. Does it answer my question?
Yeah, sir. Yeah.
Question? Yeah.
Because see, the augmented reality is the streaming problem, but image recognition might be it is not a streaming problem. You can capture the image and you can find out the features or the classification. Am I right,
Yeah.
sir?
No, augmented, you're talking about augmented reality, right?
Right. So where?
Augmented
Yeah.
reality is just superposing something on the actual. So
Right.
one of the projects my students are doing this year, we are looking at making making an image of what should be constructed according to the construction plan. So using a
Correct.
4D model, we have the BIM model with the actual
Yeah.
object, and
360
then
model.
the 4D model, you also put in the time into it, when these things are supposed to come. So we have the virtual model, and on a construction site, you point the camera, it takes the image of the actual, and then superpose what should have been there at that time. With augmented reality, you superpose, so that is augmented reality. There also, we have a lot of potential for using many of the machine learning techniques.
Yeah, challenges are there, sir. Challenges are there. You are correctly mentioned. The challenges are there. Thank you.
Nandish, I saw some messages, but I was not able to read it. It's not in the chat. Can you unmute and speak? I saw some message from Nandish. I don't see it in the chat box. I don't know. Nandish, are you there? Let me just check the chat. Okay. Okay, this was sent personally to me. Okay, with respect to brick building machine, does the machine break the brick? At the moment, no, it is still the first prototype. So you need to load the bricks of the correct size. But just the early prototype, they are just doing the first test on a construction site. Okay, right. Any more questions? Okay, in that case, if there are no more questions, we will stop today. We will start at 9:30 tomorrow as usual. Use the same link, and we will continue. Okay.
Thank you, sir. Thank you. Yeah.
Okay.
Thank you, sir.
You.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you very much.
Thank you, sir. Thank you, sir.